This tutorial demonstrates linear backlink analysis using SimXpert. A 9mm flat plate is to be analyzed to determine the maximum force that it can withstand, considering backlink only. The girder is fully constrained at one end, and at the other end it allows displacement in the axial direction. Make sure that you are in the structure's workspace. For this tutorial, use linear backlink method. First, make sure that the units are correct by clicking on Tools, Options, Units Manager. Make sure that you conform to the format shown by clicking on Standard Unit and select the appropriate one. Under Input Output, make sure that the Reduce Part box is checked, and under the mouse option, specify your favorite view manipulation and click on OK to finish. But this is sometimes overlooked. From experience, it is advisable to check the tolerance under geometry. Now click OK. Let's import our parasolid. Click on File, Import, scroll down to Parasolid and go to the directory in which our parasolid has been saved. The imported girder consists of 3 parts. You want to merge these 3 parts to form a continuous part. There are numerous ways to do it, but in this tutorial we will use a very simple approach and yet very effective with SimXpert2010. This is how I will do it. Click on Stitch on the Geometry tab. Use a small tolerance for better result interpretation. Select the part to be stitched and click Apply. It is advisable to stitch only the parts that are directly in contact. Stitch the other 2 parts, then click OK. For a better work presentation, I decided to have a uniform color for the entire girder, and it is a good practice for professional work. Follow these simple steps. But notice I've done it for all the 3 parts. We can now create the material property of the beam. Name it steel, give it a Young modulus of 200 GPa, a Poisson ratio of 0.3, and a density of 7850. Notice that the shear modulus will be calculated automatically. Then click OK. Since we are dealing with flat elements, we select Shell on the 2D element. Here we can specify the material and thickness of the beam. In the Entities windows, select Surface in the picking filter and select the model you want to specify, but here I'm going to start with the flanges. For the material, select the steel created earlier and give it a thickness of 16 mm. Then click Apply. Do the same for the web, but first clear Entities by clicking on Clear in the picking filter and give it a thickness of 8 mm. Then click OK. The shape properties are now visible in the model browser. Next, we are going to mesh the surfaces. We select the entire girder, giving it an element size of 5 cm. And because our surfaces are rectangular, we select Quad Dominance under Mesh method and click OK. Next, specify the load and boundary conditions. Zoom in the first edge of the beam. We now uncheck the rotation boxes. This constrains it for any rotations at the pin. Under Translations, leave the boxes unchecked and keep the values at 0. This means that there will be no translations whatsoever. Under Entities, select Pick Curve in the picking filter. We can now select the curves we wish to constrain. Click Apply and rotate the girder to constrain the other edge as the previous one. First clear the previous curves and the entities by clicking on Clear and deselect the translation text box. Now notice that it can translate in the X direction. This is because at this point the beam is taken to be on a roller. Notice that the beam can translate in the X direction, where at the first edge it is constrained in that direction. Click on the hatch line on the Off tab to display or hide the forces and constraints. We now want to apply the force to the middle of the beam. There are numerous ways to find the middle of the beam. Here I will use one I'm familiar with. Watch. Go to Geometry. Under the Curve tab, click from Point. Select Polyline. Notice that we are using a 2 points method. And under Point, select the 2 nodes at the edge of the plates to construct the diagonals. Click Apply and construct the other diagonal, then zoom in to view the point of intersection that is now the middle of the beam. Go to Load and Boundary Conditions, select Force. Under Entities, select Pick Node in the picking filter, and select the node in the model window. Give it a magnitude of 1000 newtons, and change the direction so that it can be applied on the beam, at the node, in the negative Z direction. Create the Nastran job, name your job, specify the kind of solution type, and specify the location where the job should be executed. Now double click on the load case control. Under eigenvalue extractions, we specify the number of desired routes. We want 5 eigenvalues to be calculated. Under result normalization method, select maximum, click apply to achieve what we've explained above, then close. We want to normalize the eigenvalues to the largest eigenvector. After following these steps, run it. This is how I check that the job is done running. Monitor the process called analysis XE. But one can always check that the job is done by checking the directories to see some activities. Once the temporary files disappear, assume that the job is done. Files that we want to see are the FO6 file and the XCB files. Open the FO6 file, check for errors. If none, attach the result in the file path, then click OK to confirm. Following steps are very important. Under Result, click on Deformation, select Deformation. A window should open with the 5 backlink shapes eigenvalues requested. You can now see the result by selecting the mode and clicking on Update. Familiarize yourself with the state plot editor, as this will enhance your abilities to understand and express your result in different plot types. Give yourself some time to view the deformations to be able to interpret the result. This is how you determine your critical backlink load. The 1000 Newton is a force specified earlier. In the state plot editor, we are looking for the lowest mode factor at which backlink occurs. The lambda of 46.526 is the eigenvalue read from the state plot editor. Hence, the girder experienced a critical backlink load of 46.526 kilonewtons. Thank you for your time. This tutorial was brought to you by S-Tech, engineering technology for better business.